So let's start slowly and carefully. When we take a fraction f of x over g of x and both f and g run off to infinity, the situation is called an indeterminate form of type infinity by infinity. Formally, we say limit as x approaches c of f of x equals infinity and limit as x approaches c of g of x equals infinity, where c could be a number or even infinity itself. For example, consider limit as x tends to pi by 2 of tan 3x over tan x. Both numerator and denominator blow up, giving us infinity by infinity. Another example is limit as x tends to infinity of 4 e power x plus 2x square divided by e power x plus 3x power 5. Again, both parts go to infinity. The key message here is infinity by infinity does not mean infinity. It is indeterminate, and the real answer could be a number, infinity, or nothing at all. That's why we need further tools like algebraic tricks or L'Hopital's rule. Now here's something fun. Not every indeterminate form shows up neatly as a fraction. Sometimes they come in disguise, and it's our job to unmask them. The first disguise is 0 into infinity. If one factor tends to 0 and the other tends to infinity, we cleverly rewrite it as f divided by 1 over g, turning it into either 0 by 0 or infinity by infinity. The second disguise is infinity minus infinity, which looks like a tug of war between giants. We combine terms into one fraction or factor out the dominant term to reveal its true form. The third is 1 raised to infinity. That's sneaky, but we use logarithms here. Limit of bracket 1 plus u close bracket to the power v becomes exponential of limit v times log of 1 plus u. Inside it reduces to 0 into infinity and then into a quotient form. So the golden rule, always first transform such exotic forms into either 0 by 0 or infinity by infinity. Only then our hero L'Hopital is allowed to enter the scene. Time to roll out the red carpet for L'Hopital's rule. It says, if f and g are differentiable on some interval around c, except maybe at c itself, and g dash of x is not 0, then we can use it in two main cases. Case 1, when both f and g tend to 0. Case 2, when both f and g tend to plus or minus infinity. In such cases, the limit of f of x over g of x as x tends to c is the same as the limit of f dash of x over g dash of x, provided this limit exists. The answer could be finite or infinite. Bonus. This also works for one-sided limits and for x tending to infinity. But a word of caution, don't use this rule blindly. If simple algebra gives you the answer quickly, you don't need to summon L'Hopital. So how do we apply this rule practically? Think of it like a recipe, as easy as making instant noodles. Step 1, check what form you have. Is it 0 by 0 or infinity by infinity? If not, stop right there. Step 2, if it isn't, transform it into one of those forms by algebra. Step 3, differentiate numerator and denominator separately. No quotient rule needed here, just differentiate top and bottom. Step 4, evaluate the new limit. Step 5, if the new form is still indeterminate, apply the rule again by differentiating once more. Step 6, if after all this it's still messy, then maybe L'Hopital isn't the best cook for this dish. Try dominance tricks or algebraic expansions instead. In short, use it wisely, not blindly. Let's put it into action with some trigonometry. Consider the limit as x tends to pi by 2 of tan 3x over tan x. Both numerator and denominator approach infinity, so we have an infinity by infinity form. Perfect candidate, differentiate numerator and denominator. Derivative of tan 3x is 3 sec square 3x. Derivative of tan x is sec square x. The new limit is 3 sec square 3x divided by sec square x. Rewrite in terms of cosine. This becomes 3 times cos square x over cos square 3x. Now let's substitute. Let h equal x minus pi by 2. Then cos x behaves like minus h, and cos 3x behaves like 3h. So cos square x is h square, and cos square 3x is 9h square. Substitute. We get 3 times h square divided by 9h square, which simplifies beautifully to 1/3. Wait, careful. It actually flips. Check again. It gives 3. Final answer is 3. Simple, elegant, and all thanks to L'Hopital. Now let's stage a battle between exponential and polynomial growth. The problem is limit as x tends to infinity of 4e power x plus 2x square over e power x plus 3x power 5. Both numerator and denominator go to infinity. Now, instead of blindly differentiating 5 times, let's be smart. Divide numerator and denominator by the dominant exponential term, e power x. The numerator becomes 4 plus 2x square e power minus x, while the denominator becomes 1 plus 3 x power 5 e power minus x. As x tends to infinity, e power minus x tends to 0, so those extra terms vanish. The limit becomes simply 4 divided by 1, which is 4. Of course, you could apply L'Hopital repeatedly, but dividing through by the strongest term is faster. Work smart, not hard. Let's try something more advanced where repeated application is needed. Take limit as x tends to infinity of x squared over e power x. Both numerator and denominator blow up, so it is infinity by infinity. Apply L'Hopital once. Derivative of numerator is 2x, denominator stays e power x. Still infinity by infinity. Apply it again. Derivative of 2x is 2, denominator is still e power x. Now the fraction is 2 over e power x, which tends to 0 as x goes to infinity. So the final answer is 0. This shows us a powerful truth. Exponentials always beat polynomials in the long run. No matter how high the polynomial degree, exponential growth crushes it eventually. Time to wrap things up, my maths champions. Today, we saw that infinity by infinity is an indeterminate form, not a fixed value. We learned how to transform other strange forms like 0 into infinity, infinity minus infinity, and 1 power infinity into usable fraction forms. We then unveiled the star of the show, L'Hopital's rule, and saw its exact conditions. After that, we learned a recipe for applying it step by step. We then solved two worked examples, one trigonometric and one exponential versus polynomial, and finally, we tackled an advanced problem requiring repeated application. The biggest lesson: exponentials always dominate polynomials in growth. So next time you face a limit showdown, you'll know when to use algebra, when to use dominance, and when to call upon L'Hopital. And that's the foundation of solving indeterminate forms of type infinity by infinity. In the next video, we will explore 0 by 0 cases with even more fun examples. Until then, keep thinking sharp, but maybe not racing infinities in your lunch break.